Welcome to this scientific exploration of swarm intelligence in nature and its revolutionary applications in nanorobotics. Today we'll journey from the natural world to cutting-edge nanotechnology. Let's begin by asking a fundamental question. What exactly is swarm intelligence, and why should we care about it? Swarm intelligence is a collective behavior that emerges from simple agents following basic local rules without centralized control. Each individual follows simple rules, yet together they create complex, intelligent behavior. The key principle is that local interactions between neighbors produce emergent global patterns and problem-solving capabilities that no single agent possesses. There's no central controller, no leader giving orders. The intelligence emerges from the bottom up through local interactions. Let's examine our first example. Ant colony foraging behavior. How do ants, with their tiny brains, find the shortest path to food sources? Consider an ant colony with a nest on the left and a food source on the right. There's an obstacle in between. Individual ants explore randomly, but something remarkable happens. As ants walk, they deposit chemical pheromone trails. Other ants can detect and follow these trails, with a preference for stronger concentrations. Initially, ants explore both paths around the obstacle. The shorter path gets traversed more quickly, so more ants complete the round trip on that path, depositing more pheromone per unit time. This creates positive feedback. More pheromone attracts more ants, which deposit more pheromone. The colony converges on the shortest path through this self-organizing process. Crucially, pheromones evaporate over time. This allows the system to adapt to changes and prevents obsolete solutions from dominating forever. We can model this behavior mathematically. Let's define the probability that an ant chooses a particular path. The probability Pij of moving from node I to node j depends on tau ij, the pheromone concentration, raised to power alpha times eta ij, the heuristic desirability such as inverse distance, raised to power beta, divided by the sum over all possible next nodes k. The pheromone update rule, tau ij at time t plus 1 equals 1 minus rho, the evaporation rate, times tau ij at time t, plus delta tau ij, the pheromone deposited by ants that use this edge. Now let's examine another fascinating example, bird flocking. How do thousands of birds move in coordinated patterns without colliding? Watch a flock of starlings performing their mesmerizing murmurations. Each bird follows three simple rules, first discovered by computer scientist Craig Reynolds in his Boyd's model. Rule 1. Separation. Avoid crowding neighbors. Each bird steers away from nearby birds to prevent collisions. This is local avoidance behavior. The red bird detects neighbors within its separation zone. It steers away to maintain personal space. This prevents collisions in dense flocks. Rule 2. Alignment. Steer toward the average heading of local flockmates. This creates the coherent directional movement we observe. The red bird computes the average velocity vector of nearby birds and adjusts its heading to match. This alignment creates the flowing, synchronized movement patterns. Rule 3. Cohesion. Steer toward the average position of local flockmates. This keeps the flock together as a unified group. The red bird calculates the center of mass of nearby flockmates and steers gently toward it. This cohesion force prevents the flock from fragmenting. Let's express these rules mathematically to understand the precise dynamics. The velocity of bird I at time t plus 1 equals its current velocity plus three force vectors, F separation, F alignment, and F cohesion. The separation force is negative sum over neighbors j in the neighborhood ni of the position vector rij, divided by its magnitude squared. This repulsive force decreases with distance squared. The alignment force is the average velocity of neighbors minus the bird's own velocity. This steers the bird toward the local average heading. The cohesion force is the average position of neighbors minus the bird's position, pulling it toward the local center of mass. Fish schooling exhibits similar principles, but with additional hydrodynamic considerations. Why do fish school? What advantages does it provide? A school of fish moves as a coordinated unit. When a predator approaches, the school exhibits remarkable collective evasion behaviors, creating confusion for the predator. The confusion effect. A predator has difficulty targeting a single individual in a densely packed, moving school. This significantly reduces capture success rates. Fission schools can reduce energy expenditure by utilizing vortices created by neighbors. Positions behind and slightly to the side are energetically favorable. Schools efficiently transmit information. When one fish detects food or danger, the information propagates through the school via behavioral changes faster than individual discovery would allow. Honeybee swarms demonstrate sophisticated collective decision-making when choosing a new nest site. How do they reach consensus without voting? A swarm hangs in a cluster while scout bees explore potential nest sites. Scouts return and perform waggle dances to advertise site quality. Better sites elicit more enthusiastic and longer dances. The waggle dance encodes both direction and distance to the site, and dance duration correlates with site quality. Better sites generate longer, more vigorous dances that recruit more scouts. When enough bees visit a particular site and return to dance for it, a quorum threshold is reached. Once this threshold is crossed, the swarm commits to that site and moves together. Interestingly, scouts produce stop signals that inhibit dances for competing sites. This cross-inhibition mechanism prevents deadlock and helps the swarm converge on a single choice. Now let's make the leap from natural swarms to engineered nanorobotic swarms. How can we apply these biological principles to design intelligent nanoscale robots? We're translating principles from natural swarms operating at centimeter to meter scales down to synthetic swarms operating at nanometer to micrometer scales. This requires careful adaptation of the governing principles. First, let's establish what we mean by nanorobots and why size matters at these scales. Nanorobots are devices with at least one dimension in the nanometer range, typically 1 to 1,000 nanometers. For reference, a human hair is about 100,000 nanometers wide. A typical nanorobot might be 100 nanometers in size. That's small enough to interact with biological cells, which are about 10 micrometers, or travel through capillaries. At these scales, the physics changes dramatically. Surface forces dominate over volume forces. Brownian motion becomes significant. Viscous drag overwhelms inertia. We must account for these differences. Let's examine the unique physical environment that nanorobots must navigate. How does physics change at the nanoscale? The Reynolds number quantifies the ratio of inertial forces to viscous forces. It equals density ρ times velocity v times characteristic length L divided by dynamic viscosity mu. At the nanoscale, Reynolds numbers are much less than 1. This is the low Reynolds number regime, where viscous forces completely dominate and inertia is negligible. A critical consequence. Reciprocal motion, like flapping appendages back and forth symmetrically, produces zero net displacement. Nanorobots cannot swim like fish. They need non-reciprocal propulsion strategies. Thermal fluctuations cause random Brownian motion. This randomness is both a challenge, as it disrupts directed motion, and an opportunity, as it can be harnessed for exploration and mixing. Given these constraints, how can nanorobots actually move? Let's explore several propulsion mechanisms that work at the nanoscale. Flagellar propulsion. A helical flagellum rotates like a corkscrew, generating thrust through its non-reciprocal motion. This is how bacteria swim, and inspired biomimetic nanorobot designs. Catalytic propulsion. Asymmetric chemical reactions on the nanorobot surface create local concentration gradients. The resulting diffusiophoresis or self-electrophoresis generates motion without moving parts. Magnetic navigation. Incorporating magnetic materials allows external magnetic fields to guide and propel nanorobots. This provides precise external control but requires sophisticated field generation systems. The most exciting applications of nanorobot swarms are in medicine. How might swarms of nanorobots revolutionize healthcare? Targeted drug delivery. Imagine a swarm of nanorobots programmed to locate a tumor, penetrate its tissue, and release therapeutic drugs directly at the cancer cells while sparing healthy tissue. Why swarms instead of individual nanorobots? Swarms provide redundancy against individual failures, collective sensing to map complex environments, and the ability to tackle tasks requiring distributed effort. Tumors release chemical signals. Nanorobot swarms can implement chemotaxi, following concentration gradients of tumor markers like bacteria follow nutrient gradients to autonomously locate malignant tissue. Clot dissolution. Nanorobot swarms could mechanically or chemically break down blood clots, causing strokes or heart attacks, restoring blood flow faster and more precisely than systemic drugs. Through coordinated mechanical action, swarms could physically disrupt the fibrin mesh structure of clots. Individual nanorobots lack sufficient force, but collective action overcomes this limitation. For nanorobots to act as a true swarm, they need to communicate. But how do you communicate at the nanoscale? Traditional wireless technologies don't scale down. One approach: chemical signaling. Nanorobots release and detect signaling molecules, much like ants use pheromones. This is slow but works in complex biological environments. A nanorobot releases signal molecules that diffuse outward. Other nanorobots detect these molecules and respond accordingly. Concentration gradients encode spatial information. Acoustic or ultrasonic communication is another option. Nanorobots could emit and detect mechanical vibrations propagating through the medium, enabling faster information transfer than chemical diffusion. At the molecular level, conformational changes in proteins and molecular motors can transduce signals. DNA computing and protein-based logic gates could provide onboard information processing. What algorithms do we program into nanorobots to achieve swarm intelligence? Let's examine key algorithms adapted for the nanoscale. Aggregation. Nanorobots use local attraction rules to form clusters or specific patterns. This is useful for concentrating at a target site or creating functional structures like temporary barriers. The aggregation force on robot I is the sum over neighbors j of a weight function w of the distance, rij, times the position difference. The weight function typically has a short-range repulsion and longer-range attraction. Distributed sensing. Individual nanorobots measure local properties like pH, oxygen, or biomarker concentration. The swarm collectively builds a map of the spatial distribution through information sharing. Nanorobots distributed through tissue each measure local conditions. By sharing measurements, they reconstruct a concentration map, identifying regions of interest like hypoxic tumor zones. Cooperative transport. Multiple nanorobots coordinate to move cargo too large for a single unit. This requires force coordination and distributed control, similar to ant cooperative transport. 4 nanorobots attached to a large cargo particle. They coordinate their propulsion forces to move the cargo in a desired direction, overcoming individual force limitations through cooperation. Despite the promise, significant challenges remain. What are the major obstacles we must overcome to realize functional nanorobot swarms? Power is a critical challenge. Batteries don't scale down well. We need alternatives: harvesting chemical energy from the environment, wireless power transfer, or utilizing biological ATP if operating in vivo. In medical applications, biocompatibility is paramount. The immune system may recognize nanorobots as foreign invaders and attack them. Surface coatings and biomimetic designs can help evade immune detection. Precise navigation in complex 3D biological environments is difficult. Blood flow, tissue barriers, and Brownian motion all introduce uncertainty. Robust feedback control and swarm redundancy are essential. Manufacturing billions of identical functional nanorobots economically remains an engineering challenge. Top-down nanofabrication is expensive. Bottom-up self-assembly approaches show promise but require further development. Sensors must be small, low power, and specific. Detecting target molecules or environmental conditions reliably at the nanoscale with minimal false positives requires sophisticated molecular recognition systems. Where are we now? What have researchers actually built and demonstrated in laboratories? DNA-origami enables precise folding of DNA into arbitrary 3D shapes at the nanoscale. Researchers have created DNA robots that can walk along tracks, carry cargo, and respond to molecular signals. DNA-origami uses the specific base pairing rules of DNA to fold long strands into predetermined shapes. These structures can incorporate functional modules for sensing, actuation, and cargo delivery. Another approach: hijacking living bacteria. Researchers engineer bacteria with synthetic genetic circuits that respond to external signals, effectively turning them into controllable microrobots that reproduce themselves. Magnetic nanoparticle swarms controlled by external rotating magnetic fields have been demonstrated in laboratory settings. They can navigate through fluids, break up clots in test tubes, and deliver drugs to specific locations. Catalytic nanomotors that autonomously propel themselves using chemical fuel from their environment have been created. They achieve speeds of tens of micrometers per second, impressive at the nanoscale. Looking ahead, what might the future hold? Let's explore some speculative but scientifically grounded possibilities. Imagine permanent populations of nanorobots circulating in your bloodstream, continuously monitoring for cancer cells, pathogens, or biochemical imbalances, providing real-time health data and intervening when needed. Nanorobot swarms could guide tissue regeneration after injury by delivering growth factors, removing debris, forming temporary scaffolds, and modulating the immune response to optimize healing. Nanorobots swarm to damage tissue, clear cellular debris, and assemble into temporary scaffolds that guide cell migration and tissue reorganization, accelerating recovery. At the far frontier, nanorobots interfacing with individual neurons could enable unprecedented brain-computer interfaces, potentially treating neurological disorders or even augmenting cognitive capabilities. Beyond medicine, nanorobot swarms could tackle environmental challenges, breaking down pollutants, capturing microplastics, or cleaning up oil spills with molecular precision. Let's synthesize what nature teaches us about designing effective nanorobot swarms. What are the key principles we should remember? Keep individual nanorobots simple. Complexity emerges from interactions, not from sophisticated individuals. Simple agents are more reliable, easier to manufacture, and more fault-tolerant. Rely on local sensing and local interactions rather than centralized control. This approach scales to millions of agents and adapts to changing environments without communication bottlenecks. Embrace redundancy. Individual nanorobots will fail, but swarm-level functionality persists if enough agents remain. Designed for graceful degradation rather than perfect individual reliability. Stigmergy, coordination through environmental modification, is powerful. Nanorobots can leave chemical traces or physical markers that guide others, achieving coordination without direct signaling. Distributed sensing gives swarms situational awareness. Each robot contributes local information, and appropriate responses emerge from local decision rules without requiring global knowledge. Let's formalize swarm dynamics mathematically to understand how individual behaviors produce collective outcomes. The time derivative of position vector Ri equals velocity vector Vi. This simply states that velocity is the rate of change of position. The time derivative of velocity Vi equals 1 over mass m times the sum of three forces: internal swarm interaction forces Fint, external control or environmental forces Fxt, and stochastic noise forces Fnoise. The internal interaction force is the sum over all other agents J of a pairwise interaction function F that depends on the relative position vector Ri minus Rj. Often the interaction force is the negative gradient of a potential function U that depends on distance. This gives conservative forces derivable from a potential energy. A critical question. Do swarm algorithms converge to desired behaviors? How do we analyze stability? Lyapunov stability theory provides tools to prove convergence. We construct a Lyapunov function that decreases over time, guaranteeing the system approaches an equilibrium state. For example, a candidate Lyapunov function V of state vector x is the sum over agents I of the squared distance from agent position Ri to target position R target. If we can show that dv dt, the time derivative, is less than or equal to 0, then V decreases or stays constant, proving the swarm converges toward the target. Consensus algorithms guarantee that distributed agents reach agreement on some quantity, like direction of motion or decision variable, even with limited communication. These are mathematically proven to converge. How do swarm algorithms scale as we increase the number of agents from tens to potentially billions in a nanorobot medical application? Algorithms must have computational complexity that grows sublinearly with swarm size. Ideally, each agent processes information from only a bounded neighborhood, giving O of 1 complexity per agent. Complexity per agent should be O of k, where k, the neighborhood size, is much less than n, the total swarm size. This ensures scalability to arbitrarily large swarms. Communication should be local, not all-to-all. Global communication creates bottlenecks that prevent scaling. Local communication allows parallel processing and scales gracefully. The power of swarms lies in emergence, collective capabilities that no individual possesses. Problem solving, pattern formation, and adaptation emerge from simple local interactions. Theory is one thing, but what have experiments actually shown? Let's discuss real laboratory demonstrations. Researchers at ETH Zurich demonstrated swarms of magnetically controlled microrobots that collectively manipulate millimeter-scale objects, pushing them along predetermined paths through coordinated action. In 2019, researchers demonstrated bacteria-based microrobots delivering drugs to tumors in mice. The bacteria naturally accumulate in oxygen-poor tumor environments, demonstrating autonomous targeting. DNA-origami robots have been shown to self-assemble into larger functional structures, demonstrating how molecular-scale swarms can build bigger objects through programmed interactions. Swarms of sensor particles in microfluidic devices have mapped concentration gradients and detected target molecules, validating the distributed sensing concept. As we develop increasingly capable nanorobot swarms, especially for medical applications, we must consider ethical implications. What are the key concerns? Permanent in-body nanorobot populations that monitor health could enable unprecedented surveillance. Who owns the data? Can it be accessed without consent? Privacy protections must be established. What if nanorobot swarms malfunction or exhibit unintended emergent behaviors? We need robust safety mechanisms, fail-safes, and the ability to deactivate or remove swarms if necessary. If nanorobot therapies become available, will they be accessible to all or only the wealthy? Equitable access to transformative medical technologies is an ethical imperative we must address. Where is the line between using nanorobots for medical therapy and for human enhancement? Society must decide what uses are acceptable and establish appropriate governance frameworks. Let's conclude by synthesizing our journey from natural swarms to nanorobotic applications and identifying the path forward. Billions of years of evolution have optimized swarm behaviors in ants, bees, fish, and birds. These biological systems provide validated blueprints for engineering synthetic swarms. The unique physics of the nanoscale, dominated by viscosity, thermal fluctuations, and surface forces, demands propulsion mechanisms and control strategies specifically adapted to this regime. Nanorobot swarms could revolutionize medicine through targeted drug delivery, microsurgery, tissue regeneration, and continuous health monitoring, potentially saving millions of lives. Power supply, biocompatibility, navigation, manufacturing, and control remain challenges, but recent advances in DNA nanotechnology, synthetic biology, and magnetic control are rapidly closing gaps. Realizing nanorobot swarms requires collaboration across biology, physics, computer science, materials, science, and medicine. No single discipline can solve this alone. Success requires integrating insights from biology, physics, computer science, and material science. The intersection of these fields is where nanorobot swarms will become reality. The next decade is critical. Laboratory demonstrations must transition to in vivo validation, then clinical trials. Regulatory frameworks need development. Manufacturing must scale up. We've traced a remarkable path from observing ants finding food to engineering molecular robots that might one day cure diseases. This is the power of biomimicry and swarm intelligence. From macroscale biological swarms to nanoscale engineered swarms, we're translating nature's algorithms into transformative technologies that could redefine medicine and beyond. As we face increasingly complex challenges in medicine, environment, and technology, swarm-based solutions offer robustness, adaptability, and scalability that centralized approaches cannot match. Thank you for joining this scientific exploration. The field of swarm intelligence and nanorobotics stands at an exciting frontier where biology, physics, and engineering converge to create technologies that once existed only in science fiction.